In this video, we're going to learn a little bit about the basic chemistry of molecules of life. So everything on Earth and also everything that we consume, what we're made of, it's all made of molecules. So we're going to learn about the building blocks that make these molecules. Now, living organisms and everything around them are composed of matter, and matter, as you remember from your um, science classes in high school, that matter could be in the three different forms: in gas form, liquid form, or solid form. Now, matter is defined by something that occupies space, it has mass, and it is also composed of chemical elements. So, what are chemical elements? By definition, element is a substance that cannot be broken down by chemical reactions. So, if we take all the molecules that are around us, we can, by the virtue of performing some chemical reactions, we can break them down into their components. So, if you can think about, for example, a molecule of water, water is made of oxygen and also it is made of hydrogens. So oxygen is connected to hydrogen. So by chemical reactions, we can break these bonds that happens between oxygen and hydrogen, and then we can break them and then break this water into its components, which would be the oxygen element and hydrogen elements. But by regular chemical reactions, we really cannot break down an element into any smaller parts. With really specific nuclear reactions, we maybe we'll be able to break them down, but not by regular chemical reactions. So all matter is made up of, ultimately, if you break them down, ultimately are made of elements. And you may have seen periodic table of elements before. These all the different elements in nature has been organized into a table based on their different properties. Now, elements themselves are made of one type of atom. So element of hydrogen is made of hydrogen atoms, lithium, element of lithium is made of lithium atoms, so on and so forth. So what does it look like? So if you think about a chunk of sodium, sodium is right here. If we take that chunk of sodium, this is all pure sodium, and if we were going to zero down on this part of the sodium and break this down to the smallest possible piece that we could, which is still be sodium, we will see that this chunk of sodium is made of individual atoms of sodium. Okay, so now the question is, all right, elements are made of atoms, but are atoms made of any smaller parts? Can we kind of split atoms into different parts? Well, yes, atoms are made of what's called subatomic particles, and there's many of them, but the only ones that we concern ourselves with in this course are three of them: protons, neutrons, and electrons. There are other ones, but we're not going to talk about that. We'll leave that to the physicists. There are also two numbers that are characteristic of each element or atom. One is the atomic number, which represents the number of protons, and the other is atomic mass, which is equal to number of protons plus number of neutrons in that atom. Now, when you look at a symbol of an atom in the periodic table, you see a number of different pieces of information listed. The first thing that you notice here is the atomic number, which is equal to number of protons. Then you see the chemical symbol for the element, which is usually 1 or 2 letters. It's an abbreviation of the name of the element. In this case, we're looking at the element of oxygen, so the symbol is O. And then we have the atomic mass. These are the information that you usually see listed in a periodic table for each element. Now, you may be thinking, well, what about electrons? Atoms are made of protons and neutrons and electrons, but we've only talked about 2 of them. Well, in an uncharged atom, the number of protons are equal to the number of electrons. All right, but why does it, you may be thinking, why does it only have to be in an uncharged atom that this is true? Well, let's learn a little bit more about atoms to find out why. So here's a representation of, a very simple representation of the element of helium. Now, there are 2 pieces of information that is really important. One of them is the location of all these subatomic particles. The protons, which are represented by these symbols with a positive sign in the middle, and then the neutrons, which is represented by these 2, which don't have a positive sign, they are present at the center of the atom, which is called the nucleus. So protons and neutrons are present in the nucleus of an atom. Where are electrons, which are represented by these symbols with a negative at the center? These are the electrons, and electrons hover around the nucleus of an atom, and they're constantly moving. Okay? So protons and neutrons are in the nucleus at the center, and electrons are hovering around the nucleus. So that's the location. Now, what about what we said about this statement? In an uncharged atom, number of protons and number of electrons are the same. Well, that's because protons and electrons carry opposite electrical charges. And we know that opposite charges can neutralize one another. So if an atom has equal number of protons and electrons, then that atom is uncharged. It does not carry an electrical charge. Okay, so that's why we are saying that only in an uncharged atom, the number of protons are equal to the number of electrons. So if you have the information given to you in here in this box, and if you are told that you're dealing with an uncharged atom, that if there is no indication that this atom has charge, then you can safely assume that the atomic number refers not only to the number of protons, but also to the number of electrons. Okay, so now sometimes I come up with stupid riddles to try to help you remember some of these abstract concepts. So see if you can solve this riddle and come to our Zoom discussions to check to see if you got the answer correct. So what is the riddle? A proton and a neutron go to a bar and each have a couple of drinks. Then proton pays for its drink and leaves. When time comes for neutron to pay its bill, the bartender turns to it and says, and you have to guess what the bartender says to neutron. Okay. Now with this slide, I wanted to make sure I clear something that can be a source of confusion sometimes. Now you may run into different problem sets, different maybe textbooks, documents, or whatever, where the symbol of an atom is shown. And all this information usually is indicated, but these 2 numbers, atomic number and the atomic mass may not be placed in exact same position when you compare the symbol of the elements from different sources. So in this case, we see that the atomic number is to the left, and then the atomic mass is placed on top of the element's name. In this one, the atomic number is in the middle, atomic mass is on the bottom, which is after the element name. So don't let this confuse you. Now there are two pieces of information that you can use so you know for sure which one is which. One is that the atomic number always comes in as an exact number. There are no decimals, but usually the atomic mass is presented as a decimal number, and I'll tell you later shortly why that is. Another thing is that the atomic mass is always larger than the atomic number. Why do you think that is? I'd like to think about that and see if you can answer this. Why is it that the atomic mass is always larger than atomic number? Okay, so we've got all these elements in the periodic table, but do they all play a role in living things? Well, not all of them. The elements that you see that has been shown with a particular border, these are the elements in the periodic table that are found in living things. And you can see the borders have different colors. The ones that have a black border are the ones that are really abundant in living things. So hydrogen, sodium, magnesium, calcium, potassium, carbon, nitrogen, oxygen, selenium, phosphorus, sulfate, and chlorine. The other ones that have an orange border, these are the ones that are needed in trace amounts in living things. But that does not mean that they are not required or they're not important. So elements like iodine, if you don't have iodine, you get really, really sick. Zinc is really important. All of these different ones that are shown within orange border. If you ever buy salt and you see that the salt has iodine in it, one of the reason that salt is supplemented with iodine is because if we don't have this in our diet, our thyroid doesn't function well. You can see some of these elements that you just saw that are required in your diet because your life depends on it in the nutrition labels of the food that you commonly eat, that you commonly buy from stores. So in this case, we see calcium and iron and potassium. These are the elements that the percentage of daily value that you have to have in your food intake every day is shown in here. So next time you look at the nutrition fact, try to find these elements in this list and try to see if you can remember which ones are abundant, which ones are needed in trace amounts. Now here is a practice for you. This is basically when you look at the slide presentation and put it in present mode, you should be able to go through this, and as you click on the buttons, you should be able to let these disappear. So when I click, you see that this appears. So go through this exercise and see if you can get all of these answered. Go back to the next slide so you don't see the answers. So you go and look at the slides and go through the motions and do it yourself. So here it is, a table that I would like you to complete. Try it and come to our Zoom discussions and compare your answers with what we get when we discuss this problem. Now, isotopes. What are isotopes? Well, elements don't come in only one form. in nature, elements come in different forms, which are called isotopes. Now, the difference between isotopes is in the number of the neutrons that they have. Here's an example for the atom of hydrogen. You can have protium, in which there is no neutron, but one proton and one electron. Deuterium, there is one neutron, but notice that number of electrons and protons don't change. And then tritium, in which there is one proton, two neutrons, and one electron. So when we go from one isotope to the next, the only thing that changes is the number of neutrons. Now, neutrons don't carry a charge, and they don't really play a part in chemical bonding in elements. So in terms of the chemical properties of an atom, there's really no difference between isotopes of an element. It's just that the ones that have more neutrons are going to become heavier because neutrons contribute to the mass of an atom. Because proton is considered to have one atomic mass unit, neutron is considered to have one atomic mass unit, but electrons, their mass is negligible. So electrons are not considered to contribute to the mass of an element. Okay, so you see this number here. What does that mean? So I mentioned that each atom comes in different forms, which is isotopes, but not all isotopes are present in nature in equal amounts. There's always one that is the most abundant, and in this case, protium, for the atom of hydrogen, is the one that is the most abundant. 99.98% of hydrogen on Earth is made up of protium, and the rest is deuterium, and a very, very small amount is tritium. So why does it happen that way? Why is this more abundant? Well, because over time, the less abundant isotopes decay into the more abundant one. And different atoms do this decay at different rates. So hydrogen, let's say deuterium, it takes many, many years for it to decay into hydrogen. So is this one. For atom of phosphorus, for example, you have P31 and P32. These are the two different number of atomic masses that you have. So P32 has one extra, and it decays into P31, but that happens really quickly. So the isotopes of different atoms decay into the more abundant ones at different rates, and scientists know how long it takes for a particular isotope to decay into the most abundant one. Okay, so now that brings us the fact that there are different isotopes of an atom in nature, and there are different amounts of them. It brings us to this point of why it is that atomic mass usually comes in fractions. The reason it comes in fractions is because when scientists collect a sample of all the oxygens at any one time in nature, and then they separate the isotopes, measure their mass, and when they report the mass of a representative atom of oxygen, they average out all the masses of the different isotopes. And when you have different masses, you can imagine that you're not going to get a completely round number. So you're going to get a fraction. So if you remember, in terms of hydrogen, we had hydrogen atoms that had an atomic mass of 1, another one that has an atomic mass of 2, and really trace amounts that had atomic mass of 3. Now, these come in different proportions, but when you average out all the masses of all these isotopes, you get a you're going to get a number that has a fraction. So that's why atomic mass usually comes in fractions, in decimal point, rather than a full number. Again, here's another problem where you can click through, but if you just put the presentation in the present mode and then click through to remove these boxes, you can guess the answer and see if you are correct. So, speaking of isotopes, some isotopes, when they decay into the more common form, so let's say we're talking about carbon, the most abundant form of carbon has an atomic mass of 12, okay? But there are less abundant ones, carbon-13 and carbon-14. And when these decay into the more abundant form, they actually give off energy. And scientists know how long this takes, for example, for carbon-14 to decay into carbon-12. So that's kind of a clock for them. Now, they also know, scientists also know that this energy is coming off, so they can actually measure when an atom decays into the less abundant form. So they can capture that information. Now, since different radioactive isotopes have exactly the same chemical properties, what scientists can do is that they can introduce radioactive isotopes of an element into a chemical reaction and see where that element is going. What is it going to turn into? So let's say if there is a reaction in which carbon is taken from nature like plants do and then transformed into, let's say, molecule of glucose using photosynthesis, they can see where that carbon is going in the plant and what is it being turned into. That's one of the applications of radioactive isotopes. It allows scientists to follow chemical reactions. Now, another very important application is dating of really old fossils, because scientists know that isotopes decay into the most abundant form and they know how long it takes for these atoms to decay. Now, when they know that, then they have a clock. So when the scientists dig up, let's say, these bones, they can analyze the proportion of different radioactive isotopes. And because they know how long it takes for that carbon to decay into the more abundant form, then they can predict how old a piece of fossil is. So following chemical reactions, what happens to molecules in chemical reactions, and radioactive dating is a couple of applications in science that involve isotopes of elements.